over to you.
Right, thank you very much. It's a delight to be here. Very nice. The bar has been set very high. I have to be as cool as chess. Not sure the analogy carries globally quite as much as you might want it to be, but we'll do our best. Anyway, I'm the kind of warm-up act this morning, today. And given that we're going to be talking about game theory for this week and the week after, it's nice to have a little bit of an introduction. So some of you will have studied game theory a lot, some of you will have studied it a little, some of you may not have studied it at all. So in this first session, I'm going to run through a brief introduction to the kind of things we're going to be talking about, and although it's not going to fully prepare you, it will prepare you enough, right? So that you are able to at least, while not being an Olympic swimmer perhaps, be a reasonable swimmer in the, should we really stretch this metaphor? In the mildly non-tumultuous ocean that we're going to be swimming in for a week or two. Anyway, we'll start off with this, and then in the second session, hopefully we'll get on to some dynamics. So what is game theory? So it's a way of modeling strategic interaction. And it's a way of formally thinking about interaction when the outcomes that you obtain from what you do is also affected by what other people do. Now, there are many branches of game theory by now. It's been going pretty hard since after the Second World War. And so there's a lot of different branches. Cooperative game theory, non-cooperative game theory, zero-sum games, coordination, evolution, learning, repeated games, matching, incomplete information, epistemic game theory, that's all very philosophical, signaling, social choice, bargaining, networks, and all of the areas that people would be annoyed at me for not writing down. All of those. So this workshop focuses on evolution and learning in game theory. And as we're from a mix of backgrounds, we'll start off with the most basic concepts. So even if you know nothing, you are absolutely fine. So a non-cooperative game is going to be what I'm going to talk to you about now. And it's one way of modeling strategic interaction, and it's very simple. In fact, the simplest type is called a normal form game, or sometimes a strategic form game. And it has three things. So if you give these three things, then you have what we know as a game. And these things, conveniently, they define a normal form game, but they also appear in more complicated types of non-cooperative games. So whatever your eventual goal is, whatever the type of games you're going to be dealing with, you need to know what these things are. They're a good place to begin. So let's introduce these things straight to it. The first of them is players. That is, the entities involved in strategic interaction. So it could be everybody in this room. We could all be players. Other examples are bidders in an auction. So the people, they're deciding how much to bid in an auction. Generals facing each other in battle. Friends who wish to meet one another. Chimpanzees hunting a monkey. Algorithms that are buying or selling stock. Notice that these aren't people now, the players. The people there are algorithms. Parents applying for schools for their children. All of these are entities that are involved in strategic interaction. So that's the first part of a game. Here we have some chimpanzees going to financial trading school. Whether they would do better or worse than... Anyway, the second component of a normal form game are strategies. So each player has a set of options of what that player can do. That can differ across players. It may be that we all have the same set of strategies. It may be that we have different strategies depending on our role in the game that we face. Examples we have here are how much to bid in an auction, whether to attack the enemy at dawn or dusk, whether to meet our friend by the tree or by the river, whether to buy or sell some asset, and whether to take the risky option or the safe option in some circumstance. That could be an investing circumstance as well. So we've got 2 out of 3, we're going pretty well. The third thing in the definition of a normal form game, payoffs. So these are numbers that represent how well a player does, how well you do, perhaps, given the strategies that everyone takes. So given the strategies that everyone takes, it says how your payoffs tell you how happy or sad or something you are, and other people's players do the same for them. Other people's payoffs do the same for them. And the important thing is that my payoff can be affected by the actions of the other players. Examples are profit or loss, whether you're happy or sad, whether you win or you lose. Did you meet your friend, or did you fail to meet your friend? Did you live or did you die? How many offspring? Did you have many or did you have no children? Did you become the person you are in your dreams? All of these things are things that you might associate with success or failure, and you might want to put some numbers to measure these things of success or failure. You'll see that some of them have a kind of obvious measuring unit, right? So profit or loss, you would think of measuring it in currency. Happy or sad, win or lose, maybe less obvious, right? You could give a number 1 to win and a number 0 to lose, I suppose. Seems as good as anything. So when we write it in numbers, this is just recapping the last 3 slides. We have a set of players, N, we'll use for set of players. Each player I in the set N has a set of strategies SI, so big S, I. So over here, we're starting to do a game. We've got a game as an example. It's a prisoner's dilemma. We have 2 players. We have a row player and a column player. You can think of them as being Rowena and Colin is a common way to describe them. And they each have 2 strategies, C and D, which typically stand for cooperate and defect in the prisoner's dilemma. And finally, you have, well, not finally, but you can write the strategy profiles. So that's this product set across the strategy sets with S. So for example, in the example we have here, we have that each player has CD as their set of strategies, but the set of strategy profiles would give a strategy for each player. So it could be they both play C, it could be that Rowena plays C and Colin plays D, it could be that Rowena plays D and Colin plays C, or finally it could be that they both play D. And we've got payoffs. So we're using little pi here for player I's payoffs. Given the strategy profile small s, so small s is an element of the set big S. So here we have big S being this set. You could have, well, small s is going to be an element of this set. For example, CD is an element of big S. And the payoffs to Rowena from CD is 1. So in these matrices, which we use for 2-player games, the first number in each cell is the payoff of the row player, and the second number is the payoff of the column player. Apologies to everyone for whom this is trivial, and congratulations to everyone for whom it's not. So this is a game. We've defined a game. Fine. Let's have a few words on the interpretation of payoffs, right? What we've said so far, that's possibly the only thing that could be a little bit controversial, right? The idea of putting numbers to the outcomes. So payoffs can have different interpretations, and in different applications, they will have different interpretations. For example, payoffs could represent reproductive fitness. So how good, given what everybody does, how my payoffs indicate how good I am at reproducing. Now, reproduction can have a wide range of meanings. It could be having offspring myself. It could be reproducing people who act like me, right? It could be people copying me, having a whole host of little Jonathans copying all of my habits, right? So that's one possible interpretation, reproductive fitness. How likely are you to be copied into the next generation? Money's another very simple one. You could write a game where the payoffs are just money. Happiness, well, speaks for itself. Hard to measure, but we all know it exists, and we can all kind of say, I'm happier yesterday than I was, or sorry, I'm happier today than I was yesterday. Make statements like that. They can also describe revealed preference. They could describe what players actually choose given an opportunity. So, simplest case would be, I observe that you have a choice of an apple or a banana, and you chose to eat a banana. Right? So I think, well, whenever you have the choice to eat an apple and a banana, you always choose a banana, unless there's something else that's better. Therefore, you prefer a banana to an apple. Therefore, if there's an outcome of a game where you get a banana, I should give a higher number to it than the one for when you get an apple, right? So I'm choosing the numbers to represent your actual choices, to represent the world as I've observed the world to be. So, of course, in that case, if I'm just choosing numbers to represent, well, either how I've observed the world to be or how I would like the world to be, I should, I have some flexibility there, right? In the banana and apple world, if I'm choosing one number that's bigger than another number, there's an awful lot of numbers I could choose. So we could, in that case, we're able to arbitrarily change payoffs according to some increasing function. By increasing function, I mean, well, you know what that is by now, but in this case, it's like, say I gave the banana more in terms of payoff than the apple. So say it was 5 and 3. After applying the transformation, I should still give a higher number to the banana. That's important. In this example here, we've just arbitrarily added 3 to all of the payoffs. So you'll see that this doesn't change the ordering that we had before. So if I just pop back, you see that, say, Rowena preferred DC. She got a payoff of 4 to CC, where she got a payoff of 3. After adding 3, well, she's got 7 and 6, but the ordering is still the same. She still prefers DC to CC. Now, if you don't care about comparing individuals, you can have different transformations for each player. Because if you add 3 to each of Rowena's payoffs, her ordering remains the same, whatever you do with Colin's payoffs. So here we've added 3 just to see the previous one. We added 3 to all the payoffs. This one we've added 3 only to Rowena's payoffs. Now, if what matters is only the order of payoffs, then this is absolutely fine. Of course, if the payoffs have some meaning with regard to comparing players, then that's unacceptable, right? Because if there was some meaning here that at CC, Colin and Rowena were equally well off in some sense, equally happy, equally wealthy, if that had some meaning, then only doing the transformation where you added 3 to Rowena's payoffs would obviously change the relative payoffs. And if there was some way you wanted to interpret the relative payoffs, it would disrupt that. So what's this great digression really saying? It's saying that payoffs have several interpretations, and you want to think before you use a game about what the interpretation of your payoffs is, because that interpretation will also affect how you could play with the payoffs, how you can change them in a way that doesn't affect your actual analysis. For example, if you wanted to consider uncertainty, so let's say Rowena doesn't know what Colin's going to do. So she wants to consider uncertainty. So in that case, perhaps she doesn't just want to consider the payoff that she'd get from CC and the payoff that she'd get from CD, for example, but perhaps she wants to consider what would happen if Colin, well, some expectation. Right? So perhaps she thinks Colin will play C with probability half and D with probability half. How should she feel about that? Right. Well, it's common to assume something called von Neumann-Morgenstern expected utility, which basically says players act as if they want to maximize the expectation of their payoff. So in this case, this would say, well, Rowena should be indifferent between either, for example, obtaining a payoff of 2 here. She should like that an equal amount to having a coin toss between obtaining a payoff of 1 here and a payoff of 3 here. So that if there are 2 possible outcomes or more possible outcomes, you can consider the expectation of the payoffs, at the, well, at pure strategy profiles. You can consider that expectation and then you can compare it to other numbers. And sometimes you can do this, sometimes you can't. So this is what I mean, that as how you interpret payoffs tells you something about what you can do with the numbers. What you can do with the numbers is, of course, there's a reverse connection as well, tells you something about how the payoffs are interpreted. So you would expect that being able to take expectations of payoffs and work with them is related to the meaning of the payoffs. It's related to the preferences of the players themselves. So it turns out that this type of expected utility, von Neumann-Morgenstern expected utility, can be assumed when players' preferences satisfy certain axioms, which are known as completeness, transitivity, continuity, and independence. And, well, to give essentially these conditions say that nothing weird is happening. In this case, it would mean that if you see Rowena prefers CC to CD, 3 is bigger than 1. So you can, if you add more C to a probabilistic, so say there's some probability of CC and some probability of CD. Essentially, if you add more and more chance of this, then you prefer that, right? And another axiom, independence, essentially says that if you prefer one lottery over outcomes to another lottery over outcomes, if you mix both of those lotteries with, say, if you give them mix them with another lottery, so take a lottery and mix it with both of them, then your ordering over the subsequent lotteries is the same as the previous ordering. So if I preferred lottery 1 to lottery 2, and then I have a combination of lottery 1 and lottery 3, and a similar combination of lottery 2 and lottery 3, then I should prefer that first combination to the second combination. Now, under these axioms, we can use VNM utility, and often we'll just use that without remark. Often people working in game theory use that without remarking it, which is fine. If you think about it, when you allow expectations, that does put restrictions on how you can change payoffs without changing your problem. So if you were to just, for example, I can't change these 4s are the biggest number. So if I changed each 4 to 40, if all I cared about was the ordering of the numbers in the matrix, that would be fine. They would still be the biggest number. Of course, if I'm thinking about expectations, that changes things, right? It would mean even a small chance of getting DC would make Rowena very, very happy about a prospect. So we have to have a restriction. If we're going to keep the same preferences, keep the same VNM preferences, we're only allowed to do affine transformations of payoffs. So you take a payoff, if we times all of Rowena's payoffs by some positive number A, and then added or subtracted some number B, her preferences would remain the same. Note, it's not always the right assumption. So we mentioned that payoffs might represent offspring. So if you think of a setting where you've got generations, and imagine you are facing the choice of each generation has 2 offspring per person versus having 3 with probability half and having 1 with probability half. So if there are 2 every generation, then the population size doubles every generation. Yeah. If half the time there's 3 offspring, and half the time you have 1, well, then that's not going to be so good, is it? Because in 2 generations, imagine one gets 3 and one gets 1, well, you'll only have tripled rather than quadrupled the numbers. You can think of this as applying to investing as well. Anytime we care about growth rather than, well, if anytime we care about growth, you may wish to consider expected growth rates rather than your expectations of your actual returns in a single generation. I should add, as a side to the people who are thinking about large populations and the expected number of offspring, that if you were going to do that and you wanted to, this would refer to a situation where these payoffs of 3 or 1 were correlated across members of the population, right? So if you wanted to look at the survival of a population rather than just a lineage. So we should be careful. In this case, you really actually want to be comparing geometric means or expected logs of the payoffs, rather than just taking an expectation. So that's just a warning. We have a game. What do we do with a game after we've got it? So we've constructed a game, we're modeling a situation. What do we want to do? Well, we want to be able to say, this is what's happening, this is what we expect to happen, perhaps, or this is what should happen in the game. This is where we come to the idea of a solution concept. So solution concept takes a game and chooses a subset of strategy profiles. So it's saying this is what will happen in this game, or this is what could happen in this game, or this is what should happen in this game. It could be normative as well. It could have moral content. And yeah, what I say there, it could be predictive, desired, moral, specific, or broad. So let's go through a few possible concepts that we could consider as solutions, right? You're faced with a game. What is good? What could we look for? Or what is simple? So let's start off very simple. Say if a game is symmetric so that every player has the same set of strategies and payoffs don't depend on the identity of players, it may make sense for all players to do the same thing. Okay, we should justify that, right? Why might it make sense for all players to do the same thing? Well, they're symmetric. They're facing the same situation, right? Everyone's facing the same situation. I've got the same strategies as everybody else. Perhaps I even know that I'm facing the same situation as everybody else. So perhaps a reasonable prediction in a situation like that is that people might end up doing the same thing. So in the prisoner's dilemma we have on the right, in this example here, the two homogeneous profiles where people do the same thing are CC and DD. Formally set of S such that SI equals SJ for all I and J in the player set. Another example in which you might end up with homogeny and homogenization, where everyone's doing the same thing, is if you have some kind of process where imitation is important. Right? If you have a process where people meet people, they meet their friends, and they look at what's good, and they copy what's good. In a process like that, under some assumptions, you will typically get a dominant you typically get one strategy that grows and grows and grows and grows. So if it's kind of complementary with itself, so that if the more of something there is, the more people want to do it, typically it's going to grow. And so if people are copying other people, eventually everybody's doing the same thing. And then if everybody's doing the same thing, there's nothing else to copy. So you get stuck. So that's another justification that you might want to consider homogeneous profiles. It's a very naive concept, solution concept. Let's move on to some things that are a bit more sophisticated. Perhaps we'd like an efficient outcome. Why would we like an efficient outcome? Well, if it's inefficient, we could do better. So we think about the Pareto frontier. Is the set of strategy profiles such that there's no other strategy profile that's better, in the sense that, so we've got S, and if it's efficient, if S is efficient, there should be no S dash that does just as well as S for everybody and strictly better than S for somebody in the player set. So that's the Pareto frontier. Basically, well, if we look at this game on the right, you can ask, is DD on the Pareto frontier? And you can say, well, DD gives Rowena 2 and Colin 2. Does there exist another strategy profile that gives them both at least as much as they're getting here, and at least one of them strictly more? And the answer is yes. CC gives them both 3. So DD is not on the Pareto frontier. You can do better for everybody weakly and some person strongly than DD. In fact, in this game, the efficient profiles are all of them except for DD, because if you're at DC, you can't do better for Rowena, right? You can't do at least as well for Rowena while making Colin better off. And if you're at CD, the same argument holds. So efficiency doesn't mean that everybody does equally as well as each other. It doesn't mean they do the same thing. It just means you can't make anyone better off without making somebody else worse off. And that makes sense. Efficient outcomes make sense if you think of people as coming together to decide how they're going to play the game. So if you imagine you and your friend are deciding on some point in here, right? You're choosing a strategy profile together, right? As a group, this is your combined decision. The place it does not make sense to decide is DD, because obviously CC is better than DD. You can make an argument for the other ones. I could say, come on, of course we should play DC because it gives me the highest payoff and I'm nicer than you, so you should agree. You can make that argument, and people can make an argument back in the other direction. But you can't make that for DD. For DD, it's like, well, we're both going to do worse than we could if we agreed on something else. You could have a utilitarian solution for a game. What do I mean by that? So I think this is the typical line, the greatest good for the greatest number. Whether it's officially a quotation of Jeremy Bentham, I do not know. I should check. I've seen Jeremy Bentham's body. They've moved it now. He asked for, after his death, his body to be preserved and kept in University College London, which is where my undergraduate was, and it's kind of to inspire people. But the urban legend is that the other college, King's College, students from there at some point stole his head and played football with it in the streets. And so, at least when I was at UCL, I had well, they said it was a fake head. It was certainly a heavily reconstructed head on top of the body, which, being fully clothed, you know, you never really knew. But anyway, his idea, he was utilitarianism, effectively the greatest good for the greatest number. Now, there are a lot of philosophical quibbles about it, right? Because you can think, if you're looking for the greatest good for the greatest number, you may wish to heavily restrict the rights of some small group if it gives a great benefit to a large group, right? Gladiatorial combat or something, right? Perhaps it's a net positive. In this case, well, the simplest type of utilitarianism we could apply to a game would be to choose the strategy profiles that maximize the sum of payoffs. If you wanted to weight people differently, you could put a weighting on the players as well. So you could count some players twice as much as other players, and that would also be, at least theoretically, fine from this point of view. But the point is, you're maximizing some kind of sum or weighted sum of players' payoffs. And this should be on the Pareto frontier, because if you could move somewhere that was better for everyone, so I could tell you immediately that DD is not on the Pareto frontier, So it's not going to be the utilitarian solution because 2 plus 2 is 4. But if you could move somewhere that does better for everyone, obviously you're going to get to a higher sum, right? Because it's better for everyone. So 3 plus 3 gives you a higher sum. In this case, with equal weightings on the players, the utilitarian solution is going to be CC. Right. Although note that this solution is definitely not invariant to payoff transformations. If I increase this 4, so it's not invariant to order-preserving payoff transformations. So if I increase this 4 to 40, automatically that would make DC and CD the utilitarian solutions in this setup. Again, that's fine. It's just an interesting point to note. What else could we do? Well, we could have a Rawlsian solution. So John Rawls proposed that, well, essentially he proposed that this perfect political system or good political system would have 2 key points. The first being that it would essentially preserve some aspects of liberal democracy. And the second was that conditional on being able to do the first thing, it would maximize the well-being of the least well-off in society. But generally, economists being what we are, the first part of his prescription in his very thick, difficult to read book is, well, maybe not so difficult to read, but very thick and long book. The first part of his prescription is hard to put into maths, right? You know, it's hard to like, okay, what are these essentials that we need for having a liberal society? So because it was hard to put into maths, it tends to be more ignored than the second part, which is maximize, make the least well-off in society as well-off as we possibly can. That's quite easy to write. And that would be choose the strategy profiles that maximize overall strategy profiles the payoff of the least well-off player. So on the right, what you do to find those, you look at each strategy profile, you pick out the least well-off player. So in this case, it's either of them, and they get 2. This case, it's Colin, he gets 1. In this case, it's Rowena, she gets 1. So this minimum is 1 here, it's 1 here, it's 2 here, and it's 3 here. So we're maximizing how well-off the least well-off player is, and in this game, it's CC achieves that. Now, this is perhaps a more popular solution concept in political discourse nowadays than, say, utilitarianism is, right? You often hear politicians say, we have to think about the least well-off in society, right? What does this do for the least well-off in society? What does this do for the least, for the disadvantaged of society? I mean, that's often repeated nowadays, and of course that has criticisms as well. As my mother points out when she listens to the radio, she says they're always saying, you know, they're saying some idea, some policy, and they say, what does this do for the most disadvantaged in society? And she said, but I've got 4 children, and they're all pretty good, and I've done my best, and they're not the most disadvantaged in society. So from a strictly selfish point of view, it feels annoying to constantly have every policy filtered through a Rawlsian perspective. That's interesting. I mean, that of course can have cultural roots as well, right? But anyway, we can work with this in a mathy sense as well. So this set has a non-empty intersection with the Pareto frontier. So that sounds complicated, right? Why is it not just on the Pareto frontier? Well, here, remember that if there's, imagine there were, let's take some possible payoff vectors. So 1, 2, 21, 4, 7, 4, 4. Now, if we had those as our payoff vectors that we wanted to choose between, now the ones on the Pareto frontier would be what? This would be on the Pareto frontier. This wouldn't be because you could do better. So these two would be on the Pareto frontier. Just write PF. Whereas if you were looking at the Rawlsians, so to make things as good as possible for the poorest in society, well, which profiles do that? This gives the poorest 1, this gives the poorest 1, this gives the poorest 4, this gives the poorest 4. So these two are tied, so that would satisfy Rawlsian, and so would that. But you notice that this one is on the Pareto frontier, so whereas this one isn't. You can do better. So why would you, the Pareto frontier argument for moving from here to here would be we could make this person better off without hurting anybody. Whereas there's no Rawlsian argument, at least in this sense, because you are not making the worst off person better off. Of course, you could come up with some combination of Pareto and Rawlsianism, right? You could say, conditional on making the worst off person in society as well off as possible, we can try to be efficient, right? Or you could do the opposite. You could assume efficiency and then say, well, let's choose the efficient thing that makes the least well-off person as well off as possible. Yes, you may.
So this also, you cannot really change a payoff, let's say 1 to 10, and it will remain invariant. That's not happening here as well, right?
That's right. So you mean payoff transformations on this? Yes, that's right. If we transform payoffs, then that well, that could change the outcome, right? So, because let's imagine there's one poor person. So imagine we have a set of payoff vectors where one person is, well, we have payoff vectors and it's just me and you, and I'm always wealthier than you right now. So, well, I always have higher payoffs than you. So in that case, I'm much higher. Let's say I have 700, 600, 500, and you have just 1, 2, 3, 5. In that case, the Rawlsian solution will be determined entirely by yours. We'll choose the one that gives you the highest possible payoff. Whereas if we then multiplied all of your payoffs by 1 million, so that your payoffs are now 1 million, 2 million, well, now I'm the poor person, and so the Rawlsian selection will be determined entirely by whatever was best for me, which could be a different selection.
So my question actually was, if we look through the lens of these revealed preferences,
yes.
So in those cases, these concepts don't make any sense. Is that something we can say? Because in revealed preferences, apparently, those transformations make sense. And in solution concept, these transformations don't make sense.
Yeah, I mean, it depends the kind of, we could choose the numbers according to revealed preferences, but does what's revealed tell, I mean, Yeah, if we're going to look at revealed preferences on an individual basis and choose the ordering for each player, then these concepts are, the information we get from those revealed preferences is insufficient for these concepts to make sense, because the revealed preferences have told me the ordering of your preferences. Even if we have cardinal information about your preferences, about how much you like the banana more than an apple, and that has determined the payoffs we've chosen for you getting a banana versus an apple, that still doesn't give us enough information to compare your payoffs to my payoffs. So we would need some revelation about some aspect of collective choice. So we'd need to observe some aspect of choice that wasn't revealed by the choices of a single person. It's actually it's a good question, and it's a deep question as well. There is a literature on these topics. Please.
What about a case in which there's sort of a system of diminishing returns, where the difference between 2 and a 5 could be massive, but the difference between 2 million and 5 million doesn't really matter, in the sense that I definitely, like, 5 million is larger than 2 million, it's just I cannot really use it in any better way than I could have used my 2 million. So my preference actually doesn't change that much, but my preference definitely changes from just 2 to 5.
Yeah, I mean, this is the case where writing your VNM payoffs would differ from writing the cash amounts that you get, because that's.
Yeah, so in that case, Gaussianism would be the best thing, right? Especially when there's a large gap between what the players are getting and the preference between the differences.
So you think it would be the best thing because you would be getting a higher marginal amount of utility because you're dealing. Okay, so we have diminishing marginal utility amongst players, so that the poor people, in some sense, it means more to have another unit, whatever we're using to measure it. And you're right, that's an argument in favor of redistributing, say, let's say we have diminishing marginal happiness in money in terms of redistributing money towards poorer people. It's not quite raw. So this specification of Rawlsianism is very sensitive, because it says that even if you're the poorest person or the least well-off person, if we can increase your payoff by 1, even if it reduces everybody else's payoff by 10, assuming we're still wealthier than you after that, we should still do it. So even though the value of losing 1 to me might be less than the value of gaining 1 to you, it doesn't need to necessarily, choices aren't necessarily going to be about linear transfers like that. Okay, is that enough for now? Excellent. Okay, we're doing great for time, actually. Okay, so here, now that we've dallied amongst some of these solution concepts, so the ordering I'm going through things with you is slightly unorthodox. It's possibly, if in a standard game theory course, you might know, it's more normal to go in at this slide after telling you what a game is. But I think it's useful to realize that solution concepts they are something that you choose, and they do have meaning, right? You've chosen your model, and you want your model to model something, and the solution concept you use should be the correct solution concept for what you want to model. So we're not going straight in and saying like, it's Nash equilibrium, it's very famous, it's the one everyone uses all the time, and that's all there is. It's not all there is. And whether it's the most relevant in a situation depends on the situation. That said, we should definitely cover it. So let's start with strict dominance on this. So strict dominance is, in some sense, a fairly weak condition. So it says never play a strategy that's always worse than some other strategy. So if you have two strategies, so in this case, say Rowena has C and D, and C, no matter what Colin does, Rowena will always do worse by playing C than by playing D. So if Colin plays C, Rowena would get 3 from playing C, but would get 4 from playing D. If Colin played D, would get 1 from playing C and 2 from playing D. So no matter what Colin does, Rowena does better playing D than playing C in terms of her own payoffs. So if you imagine Rowena making a decision on her own, saying, what will Colin do? I don't know what Colin's going to do. Oh, it turns out that whatever he does, I'm better off playing D than playing C. So I should not play C, because C is dominated by D. It's always worse than D for me, no matter what the other player does. So that's the argument that underpins this idea of strict dominance. Formally, for player I, SI dash is strictly dominated if there's some other strategy, SI double dash, such that SI double dash always gives a bigger payoff. Well, that is SI double dash played against S minus I. The minus I represents everybody except for I. So SI double dash played against this SI minus I gives a higher payoff than playing SI dash against SI minus I for all possible S minus I's, for all possible S minus I's. So for everything that the other players might do, SI double dash does better than SI dash, and therefore SI dash is strictly dominated. The idea then is that perhaps you don't want to do things that are strictly dominated. Of course, this can lead to some tension, right? In this case, let's say you use this concept and you said the solution set is all strategy profiles such that no player plays a strictly dominated strategy. Well, in this game, this almost solves everything. In some games, it gives you nothing because you have nothing that's strictly dominated. But here it gives you everything. It says, well, for Rowena, C is strictly dominated, so we can eliminate it. For Colin, well, the same applies. C is strictly dominated. So all you're left with is DD. Elimination of strictly dominated strategies in this game only gives you DD remaining, which is Pareto inefficient. So in this case, elimination of strictly dominated strategies gives you an inefficient outcome. In some ways, that's almost like the definition of a prisoner's dilemma, right? It's somewhere where individual rationality conflicts with collective rationality. We take collective rationality being the rationality that underpins ideas of efficiency, then yeah, they conflict here, individual rationality. So that's strict dominance. And we can also use strict dominance iteratively. So I've changed the game here. So I've just changed Rowena's. Why have I changed the game? Because I couldn't make this point I'm about to make with the game we had before. And here is the change. I've just changed this from a 1 to a 4 for Rowena. oh, sorry, for Colin. So Colin's 1 here became a 4. And what does that mean? Well, we still have that Rowena has C, strategy C for Rowena is strictly dominated. But now, if you look underneath these, this isn't the case for Colin, because we have 3. If Rowena plays C, Colin's better off playing D. But if Rowena plays D, Colin's better off playing C. So you can't say that Colin is always better off playing D than when he plays C, and you can't say the opposite either in the original game. However, perhaps, well, what we had before was perhaps a player should never play a strategy that is always worse than some other strategy. That was strict dominance. We can iterate that. We can say, if I also assume that other players also act this way, perhaps I can extend the logic. So in this case, imagine you're Colin. So first let's imagine we're Rowena. Rowena says, well, C is strictly dominated. I won't do that. I'll do D. And then imagine you're Colin. Colin says, well, there's no dominance relation amongst my strategies. However, there is a dominance relation amongst Rowena's strategies. And I know Rowena is rational, so I think she won't play a strictly dominated strategy. I think she won't play C. So I think Rowena, this is Colin speaking, he says, I should give him a funny voice or something so you recognize him, but anyway, so Colin says, I think Rowena will not play C because it's strictly dominated. So given that now we're crossing off C for Rowena, Colin's looking at same strategies as before, but he's ignoring this part. So he's looking at a reduced game where Rowena doesn't have strategy C available. And in this reduced game, you see that Colin has C strictly dominating D, because whatever Rowena does amongst the strategies she has remaining, Colin is better off playing C than D, because 4 is bigger than 2. So you delete strictly dominated strategies for all players. So in this case, for Rowena, you consider the new game without these strategies. So this is this smaller game here, just removing this line. And then you delete strictly dominated strategies in the new game. And you continue until no strictly dominated strategies remain. So in the new game, we delete this. And all we're left with is DD. Right, so far so good, right? So you can repeat that. You can repeat iterated deletion as much as possible, as much as you like, right? Some games there'll be no strictly dominated strategies from the start, so you can't do anything with iterated deletion there. Other games, yeah, you could do several rounds because after, so you could, Rowena might delete some strategies, and then Colin might say, well, in the remaining game after Rowena's deletion, I can delete some strategies. But then Rowena, we can go back to Rowena maybe, and she says, well, I know I'm rational, so I deleted the strategy. But I also know that Colin is rational. And I also know that Colin knows that I'm rational. So because I know that Colin knows that I'm rational, I know that Colin knows that I've deleted these strategies. And Colin's rational, so he knows that I've deleted these strategies, so he should in turn delete the strategies in the next round of iterated dominance. And then we're back at Rowena, and she says, well, now that I know that he's deleted some strategies, perhaps I can also delete some additional strategies. So next up is Nash equilibrium. That says perhaps players should choose optimally given what, so holding fixed what other players are playing. So it's an individualistic concept, right? It's holding fixed what other players are playing. So in that sense, it's similar to dominance, right? It's an individualistic concept is how it's similar to dominance. The holding fixed part is not similar to dominance. So choose optimally from an individual point of view is similar to the dominance argument. Holding fixed what other players are playing is not similar because in the dominance arguments, it was for whatever other players might do. In this case, an Nash equilibrium is going to be for a specific set of strategies that other players are doing. They'll do likewise. And for a Nash equilibrium, you use the concept of the best response, which is given what other players are doing, what's the best thing I could do? And SI is a best response to S minus I if for SI, so we're holding fixed SI, so we're holding fixed what other players are doing now, and it says that given that other players are doing S minus I, the best that I can do is to play this SI. So any other strategy that I might play, so SI dash, gives a payoff that's no greater. So it's basically the best I can do given what the other players are doing. So that's what a best response is take as given what you're doing, and I choose the best. Now, if every player plays a best response, this is a Nash equilibrium. This is what we call a Nash equilibrium. It's every player is playing a best response. This is a Nash equilibrium. In the game on the right, the prisoner's dilemma, it turns out the Nash equilibrium is DD. So you could ask for CC, you could say, is everyone playing a best response? The answer is no, because if Rowena switched to D, she could do better. So CC is not a Nash equilibrium. How about CD? Well, is everyone playing a best response? Well, clearly Colin's playing a best response to Rowena playing C, but Rowena isn't playing a best response to Colin playing D. She could do better by playing D. That's not a Nash equilibrium either, neither is DC. So DD is the only Nash equilibrium. If you check the conditions, you say, well, is Rowena playing doing the best she can, holding fixed that Colin's playing D? The answer is yes. Holding fixed Colin playing D, Rowena could get 1 or 2. She'd rather have 2. So she plays D. Holding fixed that Rowena is playing D, Colin could play C or D. He could get 1 or 2. He'd rather have 2. So he'd like to play D. So at DD, both are playing best responses. D is a best response to D, and D is a best response to D. Now, in this game, well, you can, let's think about the previous thing, strict dominance, and its relation to Nash equilibrium, right? So a best response is when I'm doing the best I can given what you're doing. Now, a strictly dominated strategy, remember, a strictly dominated strategy was something that was always worse than some other strategy that I might take. So if a strategy is strictly dominated, it's always worse than another strategy, the strictly dominated strategy will never be a best response. Why? Well, I mean, it's like if A is always better than B, what would B be a best response to? If A is always better than B, if I was like, well, B is the best response to something that you guys are doing, no, it can't be because A is always better than B. A would be give a higher payoff than B does against S minus I. So if S, let's go back to dominated for a second. Yeah, if S I dash was strictly dominated, this would hold, which would mean that whatever other players played, this would never be a best response because this other strategy does better. So what does that mean? It means deleting dominated strategies, strictly dominated strategies, gets rid of strategies that will never be played at Nash equilibrium, right? Because they're not best responses. So if we get rid of strategies that will never be played at Nash equilibrium, if we end up with only one thing remaining at the end, then that must be a Nash equilibrium because it must strictly, it must, you've had this sequence of strict domination of getting rid of things that will never be played, so therefore these other things will never be played, so therefore these other things will never be played. Now, yeah, so we get left with the Nash equilibrium. In this game, well, in Prisoner's Dilemma, you have a strategy that's strictly dominant, which means it strictly dominates everything else. When everybody has a strategy like that, it's easy. It's obviously going to be a best response to anything, and therefore it's a Nash equilibrium if everyone plays the strictly dominant strategies. When would Nash equilibrium make sense? When would Nash equilibrium make sense? So it might make sense if all players have correct expectations about what other players will do, and then they best respond to those expectations. Where do expectations come into it? Well, remember Nash equilibrium is defined using best response, which is, are you best responding to what everybody's doing at the Nash equilibrium? It's like, okay, how do you know what everybody's doing at the Nash equilibrium? Well, we kind of know. We're at an equilibrium. Or we don't know, but we're just doing the right thing anyway because we're following some algorithm that makes us do the right thing. But you can think of it as procedurally the right idea about what everyone else is doing. And given that, you best respond. You do the best thing for yourself, given that you have the right idea about what other players will do. Whereas, so you see that's relatively strong, right? Correct expectations, having the right idea. Playing your Nash equilibrium strategy is usually good for you individually when you're at the Nash equilibrium. So you should know that you're at the Nash equilibrium. If you don't know that, then things are trickier. Whereas something like strict dominance is, informationally very weak, right? If I know that something's always better than something else, I don't need to know what you guys are doing to know that I shouldn't do the thing that's always worse than something else. All of the things, well, you could, if needs must, think of hybrid solution concepts, right? If you have a specific type of solution you'd like, you could take some of the things we've looked at, as we discussed earlier with Rawlsian and efficiency, and you could glue them together some way. You could assume one, then say conditional on one, let's have the other. Or you could try to combine them in some way to come up with some kind of weighted average somehow. I haven't done that, but yeah, you could try. for example, you could have Rawlsian Nash equilibria. So you could say, let's have a Nash equilibrium, and then let's choose the Rawlsian outcome within the Nash equilibrium. Let's choose the Nash equilibrium that makes the poorest person best off. So let's look at this game on the right. We have a stag hunt, and you've got stag here. So you can, basically the idea of a stag hunt is that each player has two options. You can hunt a stag now, but you require the other player to also hunt the stag for you to be successful. If you are successful, you manage to hunt the stag and you get payoffs of 3 and 3. Your other strategy, if you fail, if the other person doesn't join you, you get a payoff of 0 if you try to hunt the stag on your own. Your alternative is to hunt a hare, so a large rabbit, and definitely get a payoff of 2. So it's a setting where there's the risky option is go for stag, and the safe option is to go for hare. Now, you can apply everything we've spoken about so far, all the solution concepts to this. You'll see that the Pareto frontier is clearly only SS. Nash equilibria, there are 2 of them. There's HH and SS. Because if the other player plays S, you want to play S. Your best response is S. Best response to S is S, but the best response to H is H. You'd like to do the same as the other player. It's what's known as a coordination game. But you might want to choose within those Nash equilibria. So you've got 2 of them. If you were to say choose the Rawlsian one, the one that makes the poorest player best off, it would be SS. That gives the poorest player 3. HH gives the poorest player 2. If you wanted to do a utilitarian choice within Nash equilibria, you would end up with the same thing. Now that would be a kind of situation where, I mean, imagine you were designing, I wanted you all to play a game, but I thought you were all pretty selfish, and whatever I told you to do, you would try to play a best response. Yeah, so for yourself. So if I was thinking about that, I might think, well, given that I want to have an outcome that's stable, that you're going to stick with, and I know you're going to try to play best responses, so because I want it to be stable and I want you to stick with it, I'm going to have to suggest a Nash equilibrium, because if it's not a Nash equilibrium, you're going to start looking for cunning ways to trick the system. So perhaps I want to suggest a Nash equilibrium, like HH or SS, but there might be more than one Nash equilibrium. So given that, perhaps I would like to suggest one that has particular properties. Perhaps I would like to suggest one that's Rawlsian or utilitarian, or has the number 7 in it because it's a nice number. Whatever I choose, right? So you can do that. In a game like, something called risk dominance, which in a 2-player, 2-strategy symmetric game like this, coordination game, it's a coordination game, so there's an equilibrium where at equilibrium we all do the same thing, whether it's SS or HH. And it's risk dominant if, we both play the strategy that would be best if we didn't know anything in some sense about what the other player was going to do. Well, not didn't know anything. If I looked at this game and I said, well, let me be Rowena, and I said, what will Colin do? Given I don't know, perhaps I should think he'd randomize 50-50. If he did randomize 50-50, what should I do? Oh, I should play, my expected payoff from playing stag is half of 3 plus half of 0, it's 1.5. And my expected payoff from playing hare is 2. Okay, I should play hare. So if I played that strategy, it would be H. The other guy also does that, it would be H. So this is what's hare is what's known as a risk dominant strategy. It's, you know, safer in a sense than playing stag. Playing stag relies on, I'm depending on the other player, right, to come and hunt the stag with me. So I have to trust the other player. I have to trust that the other player is going to play stag. I mean, also, to some extent, I have to trust that the other player trusts that I'm going to play stag, right? Because if he doesn't think that, he might want to play stag, but if he doesn't trust that I will, he might not want to. And you can go a level above that as well, because if I don't trust that he trusts that I trust that he will play stag, then we have a problem. Anyway, we can have hybrid solution concepts as well. So the last thing we'll do in this...
Is there a particular reason you, the last slide, specifically mentioned 2x2 game for the risk dominant? In all of the cases, it was general for any kind of game.
There are generalizations of risk dominance that...
This definition works only for 2x2.
There are, I mean, you could give use this definition on larger games, but generally people don't. That's and there's people have worked on generalizing risk dominance. There's a definition in the original book for generalized risk dominance for many players. It's not really used. People don't really like it. Somebody else tried to come up with another version of generalized risk dominance that is quite nice. That's generally about one strategy risk dominating a lot of other strategies. So it's not quite the same. It's not simple.
I mean,
is the answer.
Looking at it, it looks like you just define these lines for higher games as an equal probability the opponent is playing.
Yeah,
That doesn't work.
the thing is when we don't have a symmetric game, so this you could just, an equal probability definition, yes, you could immediately extend it to anything and any setup. But actually, that definition is a simplification of the 2x2 asymmetric game definition of Harsanyi and Selton. So that definition is in itself a simplification of their original definition. And, so, yes, this could be, but you wouldn't want to call it risk dominance. You'd want to call it, and I'm sure people have done it, would be what, best responding to a flat prior or something along those lines. Yep, here we can. Here, if we sum, so 3 plus 0 is 3, 2 plus 2 is 4. So H is risk dominance, exactly. Same answer applies. Yes, and I wouldn't call it risk dominance. So, yes, you could. Now, yeah, I mean, there are extensions of, you know, there's ideas of P dominance. You want to play a strategy if at least a share P of the population is also playing this strategy. In this case, it's half. Right? Or if you think the probability the other player plays that strategy is at least P. In this case, that P is half. Yeah. So there are generalizations, but not on this slide. Right. Let's finish off this section with a quick bit about mixed strategies. So far, although I have spoken about taking expectations and uncertainty, I've just spoken of the uncertainty as coming from somewhere, nowhere. You can also think of a player randomizing on purpose. So a player who says, I will do stag with some probability and hare with some probability. Bear with me for now. I don't like mixed strategies either. But, yeah. You can think of someone who's randomizing. That's their strategy. And sometimes you definitely want to have some kind of randomization, or at least you want to be unpredictable, right? I mean, imagine you're playing rock, paper, scissors with a friend. Choosing pure strategy that's predictable is probably not a good idea, right? But they say 70% of people start with scissors. So I go with rock. I guess I just contradicted myself. I noticed this in Japan. Every time they have a shrine festival, they have a lot of food stalls, and people sell stuff. They sell food, and always the lady who sells the chocolate bananas, right? She gives you a round. You buy one chocolate banana, with little colorful sprinkles on it, and she gives you a round of scissors, paper, stone. And if you win, you get a second banana for free, right? So you can kind of observe what she does, right? Because she will have some idea of the statistical regularities in the population for starting the game. Anyway, a mixed strategy, a probability distribution over strategies. And you can extend the idea of a Nash equilibrium to say that, well, if the strategies that every player plays as part of a possibly mixed strategy is contained in the set of best responses to the other player's mixed strategies, then it's a Nash equilibrium. So it's basically, given that I know your mixed strategies, I know what you're going to do, I have some pure strategies that are best responses to that. And so my strategy is a mixture over those strategies. It could also be a pure strategy, but it may have to be a mixture in order to make your own strategies that you're playing as part of your mixtures to actually make them best responses as well, which is one of the weird things about mixed strategy Nash equilibrium, because you're effectively choosing your own strategy to make your opponents indifferent between the different pure strategies that are the support of their mixed strategies. Best responses are calculated using expected payoffs. In this example on the right, well, consider the following strategy. I play stag with probability 2/3 and hare with probability 1/3. Yeah. So I play S probability 2/3, H probability 1/3. If I do that, so if Colin does that, Rowena says if I play stag, I get 3 times 2/3 plus 0 times 1/3, so that's 2. Whereas if I play hare, I get 2. But 2 is equal to 2, so actually I don't care what I do now, so it's a best response to even randomize over them. And why don't I randomize 2/3, 1/3, in which case Colin is saying, well, given that Rowena is randomizing 2/3, 1/3, I can randomize 2, so why not randomize 2/3, 1/3? And that gives you a mixed strategy Nash equilibrium, because given what the other players are doing, their mixture is as good as they can do. Of course, if one of them slides off their mixture, then you lose it, right? If Colin played stag a little bit more, then Rowena immediately, her only best response becomes to play stag. So there's something fragile in some, particularly in coordination games, mixed Nash equilibria. But for games like scissors, paper, stone, they're the only Nash equilibria, right? There's no pure strategy Nash equilibrium of rock, paper, scissors. As I said, I'm not a big fan of mixed strategies, except, well, if you have a good story. You can be a fan of anything with a good story. And one is where you have a population. So imagine there's this population here, and say half of you are playing one strategy and half of you are playing another strategy. Then, from my point of view, it's as if I'm playing against a mixed strategy, right? If I randomly play against one of you, it's as if I'm playing a mixed strategy. So your attitude towards people, like if someone approaches you on the street and you're in a nice part of town, perhaps, you say, oh yeah, sure, I'll help you with whatever you want help with. But because you're assuming that the proportion of scammers is perhaps low, but in another population, perhaps it's high, and what your response is basically a response to your expectations about the strategies followed by everyone in that population. Anyway, that is what we've done, normal form games, solution concepts, and we'll start off with some dynamics next lecture. Thank you for patience so far.
Yeah, so time for some questions.
I thought you were going to say time for some like coffee, but
Well, we can have questions over coffee.
yeah, we can have questions over coffee. You can wait, and we can have questions longer. You can catch me anywhere, and yeah.
So let me delay the coffee a bit. One question.
Okay.
So when you get expected utility, you get it from the axioms. So when you talked about the expected log utility, does that also come from some set of axioms or something? Or that's ad hoc?
I mean that's toys you're talking about growth, basically. I mean it's that would be where you're asking what's the well, what's your expected long-run growth of a portfolio, for example? So I don't know if it's ad hoc. That would just be asking the question, if the gambles I'm taking, the payoffs from these gambles to alternatives follow these distributions.
So probably I'm asking, is there an axiomatic formulation behind expected log?
That's a good question. Not as such, as far as I know. I just see it as a kind of solution to maximizing growth. Yeah. I mean, if you could always say that, well, yeah, just transform your utilities, and now you can work with expectations in the